Yes.
Hi, everybody. It's great to have this opportunity to talk. I will start my screen sharing in a moment. In case people didn't read the background about me, I work in what I call my day job for OpenSci, which is an organization very aligned with correlating their principles. They are improving the world through science and particularly through open source software. I'm at heart a software developer. I consider myself that, and I also am co-founder of an organization called Active Transport Futures. A lot of what I will talk about will extend from the work involved in them. Active Transport Futures is mostly a bunch of academics, or a bunch of mostly academic people, and we're trying to kind of develop a more sustainable fund model, which is a code word, if you like, for becoming semi-commercial enough that we can sustain our software development. Okay, I'll now try and share my screen and get going here. There we go. Can everybody see that?
Yes, perfect.
Okay, great. So, as it says there, OpenSci Active Transport Futures. I am contactable a whole lot of ways listed there on the right, and on the left are mostly GitHub organizations and myself as well on GitHub. My surname is Padgham, and on GitHub I'm mpadge. So that thing over here in the middle is pronounced mpadge, and that's where I do a lot of my work, as well as OpenSci and AT Futures and other organizations. On GitHub, I work exclusively openly, so everything that I do on a daily basis can be seen mostly on GitHub as well as other places. When I say me, I don't mean just me, of course. I mean a whole lot of collaborators. The work that I will talk about this evening has been supported by the contributions of a whole lot of people. Many of these are members of AT Futures or other affiliated organizations or OpenSci, or just other general people who contributed to the software that leads to the kind of stuff that I'm going to be talking about this evening. Briefly, so Active Transport Futures, briefly described already. We are committed to helping to transform cities using open data and open source software from situations like this. Some people might be able to recognize that as Amsterdam, the cliched city that everyone points at and says a city does not develop a pedestrian and bicycle culture of its own. I mean, it doesn't inherently have it. You have to work for it. That was Amsterdam, and they've worked really hard to get rid of that and done a great job. We are interested in extending the ability of open source software and open data and open planning tools beyond European and global north cities such as Amsterdam into anywhere. Oh, sorry. Slide backtrack. The next slide was supposed to be the transport futures are the transitions from that to that. That is a picture of the city of Münster, where I live, and that's the at least locally famous Promenade, which is an exclusive bicycle pedestrian path that encircles the entire inner city of Münster. Yeah, so we're working just beyond the European and global north environments. This is a picture of another city that has been doing amazing developments in planning cycle infrastructure. In this case, it's Kuala Lumpur, the capital city of Malaysia, and a typical bike lane there in the middle of the city. And we're also interested in mobility analysis and mobility support for anywhere on the planet, including places like this, which is the city of Mysore in India, where will never be put in place because they don't have to be. Bicycles own the roads there. People already own the roads there. It might not look like it, but in a sense, this is effectively a lot of what a lot of modern mobility planning is aiming for. Cities where people and bicycles, and I think if you look closely, you can probably see chickens. There are also monkeys there, own the streets, and there is hardly a car to be seen anywhere. So these are the kinds of futures that we're talking about, whether or not that looks like the sort of future other people might have in mind. Okay, I won't talk about this at all much in the next few minutes, but this is a brief description of the work that we as Active Transport Futures have been doing in collaboration with the World Health Organization. The future of this work is uncertain owing to uncertain future of many aspects of the World Health Organization for reasons that I am not keen to discuss, but are very related obviously to financial decisions in the WHO, and I have no idea what's happening, but we were working up until recently on a project for the WHO where they were very interested in the health of cities as a whole, and in particular in healthy mobility options for global cities. So as part of that, they employed us as expert advisors to develop methods for analysing and planning for healthy mobility patterns in cities. And the key there is particularly on the fifth point of there, which is effectively what we did for them and what we still do in other situations, which is to analyse dynamic interactions between movement, air pollution and health. And our specialty there is analysing the dynamics of movement throughout cities. Not going to talk about any more of that in particular, but the point is that most of that work is supported by our software. So we primarily consider ourselves, we hope to become the kind of go-to place for open source software for urban planning, and particularly for mobility planning. And we have a lot of software, almost all of it developed in the form of R packages, programmed in a variety of languages, but eventually wrapped around the language R, which has a really great user community and user base and a much lower barrier to entry than other computer languages. So we have an awful lot of those that support our work. And now on to what I was going to talk about, which is lessons in mobility data. So I just want to now spend about 2 minutes on each of these points and just try to sort of highlight some high level lessons that we've learned in developing the software that we listed for the work with the World Health Organization, and also other work that we've conducted as well about mobility data, and focusing particularly on developing analyses or data forms or software for or in ways that are as applicable as possible to as much of the world as possible. So that's kind of the key of the message that I'm trying to convey here, and the key, I think, of what we've learned in developing this work. So without further ado, to briefly step through them, be open in terms of source and data. I've got some text points here. I'm not much of a fan of screens full of text, so I won't subject you to any more than what you've already had. These are mostly here so they can be clicked on. And if I click on this, open data, it'll show you our primary source of data for all of our analyses, which is, you can see up in the top, OpenStreetMap. This here, you guys may have seen up here the writing that this is a portion of OpenStreetMap from a portion of the world that happens to be, if I zoom out, in the middle of North Korea. North Korea is very well represented in OpenStreetMap. It's an amazing database for the planet to compare a couple of slightly older images that I won't go live. This is from a commercial provider of online maps listed on the top right. There's nothing there whatsoever. This is from perhaps one that people would be more familiar with or mostly rely on. There's also very little there. And this shows that these kinds of data that people think are open, in both that company named at the top left and that named in the middle of the bottom, are open only in the sense of being accessible. They're not actually open, and they're very politically defined and politically constrained. There are political reasons why there is so few data on those maps. OpenStreetMap doesn't suffer any of those. It's truly open data, and it is the backbone of everything that we do. So use open data so that others can do that too. Open data is the best way to ensure that your mobility work will be usable by as many people in the world as possible. Use and develop open source code. As said at the start, this one just clicks through to one of our packages. Every single package we develop is open source. They're all available on GitHub, but we are committed to true openness. Some people have issues with GitHub, just as I have issues with other mapping platforms, and GitHub is not available universally around the whole world. So for example, we ensure openness, or we enhance our openness by ensuring that all of our software, if you scroll down a bit, installation, it has lists of places where all of our software is stored. And these are all source code hosting organizations. So not just GitHub, Bitbucket, GitLab. This one up here is called SourceHut, which is completely non-profit and independent. And all of our source code is mirrored on all of those. So anyone who has political issues or actual issues accessing GitHub or using GitHub is perfectly free to go to any other of these to access our source code. So that's another example of our openness that we pursue. And the motivation to do this is to try to make our work applicable in as many other parts of the world as possible. So that is what openness is about to us. Point number 2, be flexible. One example of flexibility is a package of ours, which is called GTFS Router. I'll click on there to go to the source page site on GitHub, just because it explains up here what it is: a routing and analysis engine for GTFS, which is General Transit Feed Specification Data. These are the data these are one form of data commonly used to represent public transport schedules and timetables. So this package can help you to analyze public transport systems based on the data from their timetables. This package, like all of ours, differs from a lot of open source software that offers similar capabilities, in that our focus is on analyzing entire cities and aiding the planning of mobility for entire cities. So there are other open source, for example, routing engines for GTFS data, and they will tell you how to get from one point to another. But this is, at the moment, the only open source routing engine that is explicitly developed to tell you how to get from everywhere to everywhere within the entire system and to aggregate statistics about that. So that kind of emphasizes the focus of our work on really large scale entire city analyses rather than individual A to B sort of analyses. So we have a number of other routing engines that do similar things as well. But what I wanted to emphasize was that, going back to this screen here, that the GTFS router package has been developed with extendable core algorithms. So on the surface of it, and for anyone using it directly as it is there, it interacts only with this GTFS format, General Transit Feed Specification. And there are a lot of other GTFS-based software solutions out there, but we developed our package to make sure that the core algorithms of it did not expect necessarily that input format into them. So the entire algorithmic development effectively happened by quarantining off the core parts of it and presuming a generic form of input to those, and then translating GTFS into that generic format to make sure that we can always extend and adapt the algorithms behind it to other situations and other locations. One really good example of this is some work that we did with the World Health Organization in the city of Accra, which is the capital city of Ghana. And Accra has an informal public transportation network. It has no rail systems and no subways, but it has buses everywhere. These buses are regulated by the city, but not in the sense of running to regular timetables or stopping at identified stops. But OpenStreetMap, on OpenStreetMap, you can find a list of places where the bus system stops. And that in itself was put in place by a large project to map the informal stops onto approximate locations and sort of work out where they would be. So you've got this situation where you've got a massive informal bus network that runs to all sorts of crazy schedules in locations where you can't even necessarily know where it'll stop. And what we did for Accra was to then work out a separate algorithm to process the information that we had into a format that was compatible with the core algorithms of the GTFS router package. And that enabled it to be extended and applied in an area that doesn't even have a public transport system with any regularity that likely any of us listening right now would identify as necessary for a public transport system. But it was still able to be extended and adapted to that location. So it's really important to be flexible, and particularly in thinking about not constraining your analytic procedures to one particular form of input data. So I talked, or I said the title of the talk, I forget what I've said now exactly, but about a world in which data are not equal, mobility data are not equal. And I'm not going to talk too much about that, but there are a few links here that I'll click on. Other GTFS-based algorithms are not extendable. This is a really strong example of the inequality of data. This is a thing called traveltime.com. It's the only, one of the very few other GTFS engines that's capable of the kind of many-to-many statistical analysis of an entire city. This is what the front page looks like. And you'll see the importance here. It says CWES reachable within 30 minutes from London by public transport at 1 p.m. There already was a huge push prior to the whole COVID COVID-19 situation that we're living in, and that's enormously exacerbated discussions and planning for so-called 30-minute cities. The idea being that everybody should be able to live within 30 minutes of where they need to do stuff. They should be able to live within 10 minutes of getting a, depends on which country you're in, some countries say pint of milk, some countries say beer, but 10 minutes of getting the things that you need, and 30 minutes in terms of your daily activities. And that's why that 30-minute diagram is there. So this travel time offers that. It's the world's leading provider of these kinds of services based on GTFS data. And just ignore it for a moment. I'm going to scroll all the way to the bottom, down in the mess, and you'll see at the bottom, the usual kind of structure of this website. What you've got here is a whole lot of pricing, 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 pricing statistics. This is a very, very commercial service. It's very, very closed. And if you go to the travel time analytics page here, you scroll down, it tells you what the sort of stuff you can get, and says here, supported countries. And because their algorithms are not extendable like we've made ours, they can only provide support in countries that have input data in the formats that GTFS, well, in the strict GTFS format, and hardly any other formats whatsoever. They've done a bit of effort to convert. The UK, for example, doesn't use GTFS. They have a slightly different format and have used converters there. But other than that, I won't say anything about the representativeness, demographic representativeness of these cities on the global scale. I trust that that's sufficiently obvious to everybody listening. So making algorithms extendable is really important to be globally relevant in planning for mobility. Okay, next lesson, identify the underlying issues. I'm aware that we're approaching 25 past, but we started slightly late, and I won't take too long for the rest of them anyway. Okay, identify the underlying issues. The point here is that many mobility problems, as I said at the start, there are the consequences of people attempting to apply solutions beforehand. The reason that a lot of cars today, a lot of cities today are so choked up with cars is because people planned for vehicular or automobile infrastructure in order to get people between different points in the city and primarily into the middle of cities as efficiently as possible. That was a problem that people couldn't do it. Planning for cars was a very efficient solution at the time. The consequences became apparent much later. The issue that should have been solved wasn't necessarily getting people, or in retrospect, getting people into cities quicker. We're now looking at one consequence of thought that that was a problem that should be solved, is that the entire world is interested in getting more people to walk. If you click on that one, getting more people to walk leads to things like this walk score, so-called walk score. This is a website called walkscore.com. This emerged from a very intensive, very highly funded pure academic research program into how to get more people to walk. And they came up with an idea of scoring neighborhoods and giving them a quantification for how walkable a neighborhood was. The picture right on the front there is the middle of the High Line in the middle of Manhattan. And you can't see here, but if you go, if I make this smaller, you can see the tab up the top of the web browser says find apartments for rent. And it's turned into a completely commercial service. And once again, you can scroll down and look at where this is applicable, and it's just like that other system. So that shows, well, that emphasizes the former point, and this image here also reveals that getting people to walk is not necessary in most of the world. Most of the world does walk. Most of the mobility trips made on the entire planet are walking trips. Very, very few trips are made in cars. Cars have really got very little to do with global mobility or global mobility solutions. Making walking safer and cleaner is necessary everywhere. So the underlying issue shouldn't be thought of as getting more people to walk. It should be thought of as making walking safer and making walking cleaner. If you do those, more people will walk anyway. So identifying the underlying issues, first of all, is important. Avoid unintended consequences. Unintended consequences are, the classic example is Strava Metro data. I'll try and hurry up through the rest of this. I don't know if people know about Strava Metro data. Strava is an app where you can put your fitness tracking device on and then upload all the statistics to Strava, and it analyzes all of those. And they have this thing called Strava Metro, which they claim The data set is the largest collection of human-powered transport information in the world. They're probably right. It's also very, very, I'll say well known, that these data reflect the movement characteristics of middle-aged white men, regardless of where in the world they are. They have really good representative densities in an awful lot of the world, not dominated by white middle-aged men, but analyses of these data have revealed that the data do reflect that, with all the consequences of restricting your analysis of mobility to those kinds of data only. Streets built for men have unintended consequences. So not just men moving through them, but building streets. If I click on there, that goes to an amazing web page called equalstreetnames.berlin. That's not the actual web address, but it takes a while to load, but it gives you a picture when it does of Berlin, with the streets colored by whether they're named after men or whether they're named after women. And I presume most people who will be listening will be familiar enough with Berlin to not be surprised if and when this finally gets to load, that there, of the streets that are named after people, almost all of them are named after men, and very few of them are named after women. This is important because it reflects the male-dominated planning of cities, in particular historical planning, and that has really important consequences for mobility. Mobility patterns for women, for example, in this context, can be very different to mobility patterns for men. Women can feel much more threatened. Women can literally be much more threatened in a lot of spaces compared to men. And that's very important to consider. And building streets only for men and using data only for men is not a good way to avoid unintended consequences. An example of one contribution that we're making towards it is, again, on GitHub, a bit of software called gender conscious routing that allows you to plan a route from A to B along streets preferentially named after women rather than men. There's a whole lot of other things in the pipelines for what this thing will hopefully be able to do. It's still a work in progress, but it's meant as a symbolic indication of the kinds of things that people should be thinking about and which are technologically possible now. Okay, the last point, where is generally not that important. That's kind of tongue-in-cheek in mobility data. Obviously, where is really important. Okay, I've lost that slide there. That's okay. I can go to this one. This is another project of ours, which is a website called movability.city. This is very out of date and hasn't been updated for a couple of years. But if you go to Move Me, it says movability maps. These also don't work. Munster, Germany, which is where I live. If you click on it, well, it sort of works, but the background doesn't come up. So this is a map of Münster in Germany. And the colors and thicknesses of the line here reflect the extent to which it's easy as a pedestrian to move around and there's stuff for a pedestrian to do. Now, what happened in developing this and the map that, the image that I was going to show previously that didn't work, which was an analysis of pedestrian traffic through the entirety of New York, of Greater New York City, is that what you find is that the mobility data fed into movability and the map of New York that you don't see here, but which we did partly for the World Health Organization work, are really detailed, but then there are a whole lot of gaps because you can know where people are moving, but what actually turns out to be much more important is understanding why they're doing it. And the why most commonly can be quantified if you know what sort of structures your city has. You can group whys into various categories of people move because they've got to go shopping or they want to visit friends or they want to engage in some sort of entertainment. But unless you've got information of where the kinds of locations are where those sorts of activities happen, you won't be able to generate a sufficiently accurate mobility analysis. And that's the problem that has prevented the kind of finishing of this movability idea, but which we're working on a solution for. And emphasizes that, again, OpenStreetMap turns out to be one of the most important sources of mobility data for us, and I think for the entire world, because you can put not just streets in OpenStreetMap, or ways as they say, not streets, because everything's not a street. Not everything is a street, but also building structures and building purposes, and being able to put those in then enables you to combine OpenStreetMap data with typical survey data that explain why people move between large areas for different reasons, and that enables ultimately the best kinds of analyses that are transferable across the entire world. And that's about enough for me. A few minutes over time. Thank you all.
Oh, that's fine. Yeah.
And again, there's some contact details and links to source code and stuff like that. Thank you very much.
Nice. Yeah, thank you. Thank you so much. That was very interesting. Let's just think a bit. Yeah, so maybe we can have like 2 or 3 questions now, and later we can maybe have some more if we have time. So I forgot, of course, if you have questions, you can put them into the chat. I also put down 1 or 2.
Okay.
So let's just wait maybe for if people write something in the chat. Otherwise, I will just claim my spot. Yeah. So I'm monitoring the chat. But yeah, I had the question. So what can we do if we? I mean, I certainly believe a lot of what you said. But what can we do to contribute to? I don't know, to contribute to mobility data research, or to how can we contribute our own data if we want to? If we don't want to go to Strava or something, how can we yeah, contribute to this? I think OpenStreetMap is always good, right? Contributing to OpenStreetMap is preferable.
Yeah. Yeah, although contributing is not as important as it was these days. The largest contributors over the last few years to OpenStreetMap have been Facebook and Apple, and Google aren't far behind either, which is interesting and probably just fantastic news for OpenStreetMap. It shows the importance of OpenStreetMap even for companies like Google that have their own mapping service. There's a lot of discussion about why they would do that. But the contribution aspect is then with that not as important as using it and publicizing it, and especially using it. I mean, OpenStreetMap collects statistics about usage, not in the way that Google does, not in the invasive way, but the more that it gets used, the more that it gets talked about, the more there will be impetus on OpenStreetMap to continue their public relations exercise. Helps more of the world use OpenStreetMap. And I think that is the most important tool.
Yeah. Yeah. Does it also count if I use OpenStreetMap through like a third-party app? Because I don't think they have like an app, right, for the phone, do they? I don't know, because I use OpenStreetMap if I go hiking, because it's so superior to Google Maps in that case.
Yeah, I mean, there are lots of apps. Maps.me is a really fantastic navigation one, and then there's the whole Oryx Maps world.
Yeah, you also mentioned like surveys in the end. Do you can you name a few if people wanted to look into that? What kind of surveys there are? So, or are there no standard big surveys like?
There are no standard global big surveys at that level. Surveys are always national. A lot of what we use is also population density data, and there are global sets for that. And that's an important thing because you need to know the population densities of where people are coming from and going to. And survey data are all nationally collated. There's no such thing as an international survey in that sense. Germany, for example, has really good survey data. It has this socio-economic panel data. SOEP. That provides really, really good data. And Germany also releases a lot of survey data open source for open data.
Nice. Okay.
Typically, it's your origin destination data. People fill out travel diaries. People get selected and they fill out travel diaries over a period of a week or something like that. And they say, today I walked 10 minutes here because of that. Today I drove 2 hours to there because of that. And then the government authorities that coordinate that then aggregate it up into areas, and they say this many people moved from area A across to area B for reasons of work, and this many did it for reasons of education or whatever, and they give demographic of them.
Nice. Yeah. Maybe Marcus can later talk a bit about the analysis that they've been doing of the Spanish Madrid data, but maybe that's for the after the talks. Okay, thank you, Mark. If there are no other questions, but nobody was commenting. Yeah, so we'll talk again in the Q&A and in the discussion. And then, yeah, thank you so much for this talk. Was really interesting. Yeah. And then Pia, maybe you can come up.
Yeah. So, hi, I'm Pia. I'll also share my screen in a minute. Okay. Okay, so yeah, I study math at the Technical University of Munich. So I'm part of the local chapter Munich of Correlate. And I'll talk about counting vehicles and measuring air quality and pollution today, which will only be a quick presentation, but I just thought that emissions should be part of a meetup about mobility data. And so I have a new job as a working student in a company where everything is about emission data. And it will probably or maybe sound a little bit like an advertisement for the company, but I'm not paid for this. I just like the job, my new job. And so the company is called Hodor. It's a startup and the name is Arabic and means air quality. What they do is they measure air pollution with sensors and satellites, and they also make predictions with time series analysis. Well, but my job is not directly working on air quality measurement, but only indirectly. I am developing or helping to develop the back end of a traffic counter for a German city. So it counts how many cars, bikes, buses, motorbikes, trucks, and vans there are across the city at each point of the day. And it works through video processing and cameras, which are located throughout the city. And well, actually, I'm not involved in the video processing part. Well, also, I've only been working there for not a long time. So I've been working on processing the data from the cameras such that they can easily be visualized. But I won't be talking about the technical details any further. I just want to highlight what cities can learn from measuring air quality and counting vehicles. So this chart at the top shows you how many greenhouse gas emissions were produced by what in the US in 2018. I know like this is just US and just one estimation from one data source, and maybe, for example, the percentage of emissions from agriculture may be a little bit higher or much higher, at least some may argue so. But I think representative for Germany as well, for example, or other countries, I don't know. And it's completely clear that a lot of emissions are caused by vehicles. So the percentage that are caused of emissions that are caused by vehicles is the dark green part, so the biggest part. And especially from among these vehicles, on vehicles like have the biggest parts, like here, the cars and in dark green and trucks in light green. And well, all these gases, they do not only cause problems with global warming, but also with health. Well, maybe in German cities, where like how Hodor is starting in Germany, they have some sensors in Ireland, but like they're starting in Germany. So in Germany, it's not as bad as in some Asian megacities, but also in Germany, it's important to be sure when to act. And if a German city wants to act and reduce vehicles in areas with a high concentration of toxic or unhealthy gases, they somehow need arguments for that. So they need to precisely measure concentration in the air and make predictions. But for the cities, it's not only about making bans for certain vehicles in highly concentrated areas. It's also sometimes about avoiding them if they are not necessary according to their standards. And they also have other methods to reduce vehicle emissions. One would be, for example, I'm just picking one, to increase the time span where traffic lights are red, such that drivers get just so annoyed by the longer driving and waiting time that they will use the train next time. And also in the long term, it will be interesting to know from a scientific and especially social point of view, to know if there will be more bikes on the roads when people get more environmentally aware, and how gases like, for example, sulfur dioxide are going to reduce at the same time. And I'm not showing the Hordauer dashboard, which can also be used by single persons. But so just that you can imagine, it shows either a map with gas concentration, or it shows the gases that you wish to see at each point of the day at any location in the city, plus the number of vehicles on the graph so that you can compare it. And this sounds like an advertisement a little bit again, but it's a nice interface. And Hordauer, I mean, data science is like, it's also about visualization and making everything user-friendly and easily accessible. And I know, like, this is like, I'm talking about a company, so it's not directly open source data, but like the cities, they can buy the Hordauer solution and then make it accessible to anyone who wants to know about the data. So yeah, I think data science is also about that, and I hope to be involved in the visualization part as well one day. And I know, like, this was very short, and I don't know if you have any questions, but if you have any, then just ask me.
Yeah, thank you. There was some questions. Yeah, first of all, Pia, thank you so much. Blah, blah, blah. Will the data of the vehicle counts be available? No, Markus answered his own question. And
Yeah,
then
okay.
Zola said, who are the end users of this product? Typically like policymakers or like administration?
Yeah, so it's the city, like there's like for example, Munich is the city of Munich, that's policymakers. For them, like they are one part of the end users, and so for them to decide about about the diesel, sometimes about diesel vehicle bans, for example, or something like those making traffic, making red light time spans longer, but also like it's a possibility for them to make the data easily accessible to their citizens, or to anyone who is interested in their city. Yeah.
Then there was a follow-up question. I don't know whether you know that, what kind of sensors they use for the pollution?
So I've only not been working there so long, but they are using a relative, like, I know that their cities already use some sensors themselves, but however, they use a relatively cheap solution so that it can be like put into practice easily. I don't know, and yeah.
Okay.
But I don't know exactly. Is there?
So the question is there an up-to-date data set of CO2 emissions available? It would be interesting to see the impact of COVID on emissions. So you mean over the year.
By one city, like for one city?
I don't know, probably. I mean, it's
or globally.
Globally. Also, so they are only doing it for single cities, and also they are relatively new. Okay, maybe I'll share that the city I'm doing the traffic counting for is, okay, I don't know. It's Mainz, and I hope that they will share everything once it's available.
Yeah. Maybe we can also talk about different data sources later, because I think that's, I mean, if we have time for that. Okay, and then there is also one question about the process. I'm not sure whether you're informed about that. Does installing sensors in cities have to be approved by city governments?
So by city, I think it's like done by the part of the city government, bought by part of the city.
Yeah, I think it should be, right?
To be approved, like especially if you want to put it up at lanterns or something.
Like we are working on a project where we put like a bunch of sensors here on the Straße des 17. Junis. And this was 2 years of discussing how to put sensors, what RAL color to make it, and things like that. So it's not, can't just put it up.
Yeah. Okay. Thank you, Pia, and it was really interesting to hear from your job, and hopefully you will have lots of fun in the next few years working there. Okay, then Markus can share his screen.
Okay, is it the right view?
I don't see anything.
Oh, right.
Oh, if you need me, if you can also send me the presentation. It doesn't work.
No, it works.
Ah, now it works. Yeah. Yes, we see like, yeah, that's perfect. Perfect.
Okay, cool. Yeah, thanks for being here. I'm Markus. I joined the local chapter in Berlin meetings the first time, I think, when it was still the last time in February to meet in person. Since then, I've been attending regularly some of the online ones. I'm working as a PhD student at the TU Berlin in a team where I'm responsible, like we're like a big computer science institute, and I'm responsible for a small group of PhD students, master students that are working where computer science meets the energy system. So we use machine learning, AI, and so on. That's what we usually want to do. Actually, today I'm not talking so much about AI topics. It's more about like simulation, optimization topics that we've been working on, and where we needed mobility data and had a lot of trouble getting it, because like, as Mark said, it should be open, I think. And now that I've seen, for example, the Barcelona data that we already mentioned, I wish it were like that for Berlin, for example. But I don't know any sources. So if you know any others, then, or the vehicle counts of Kia would also be great for what we are doing. And today I'm talking a bit of how data like that can be used. Yeah, I have similar slides like Pia just showed. So we all know there's climate change. It's a big problem. And if you look at the other sectors, they're at least having a small downwards trend. I mean, it's by far not fast enough, but the transport sector is actually doing the exact opposite. It's going up instead of down. So that's not good. Similar breakdown like Pia showed. If you then look at this transportation sector, like 70%. So this is EU data. I'm sorry for this bad graphics, but it's exactly as posted on this website down there. So it's not my plots. So yeah, 70-something% are from the road. So we have to change something about this. Of course, I'm totally with Mark. Part of that should be going on bicycles, walking more, and so on. So there's a lot of topics that we are not so much doing our research on. We are kind of assuming, let's say, for 2030, 2040, some sort of scenario that city planners like Mark came up with. And then we are looking at what would this mean if the now combustion engine cars are exchanged by electric vehicles. So that's actually where there is some good news. Now in 2020, I've had the slide now for 2 or 3 years recent updated. And now finally, I would say we are starting this hockey stick curve of sales of electric vehicles. So this is now the first time that it actually doubled in 2020, the last year. Last year it was already also looking a little bit good, but before that it was rather slow with electric vehicles. I mean, we still don't have the 1 million cars that Angela Merkel promised us in 2012, I think. But at least we are not orders of magnitudes away anymore, which it looked like 2 or 3 years ago. So yeah, like I said, I don't think electric vehicles exchanging one-to-one to normal cars is the solution, but let's for now assume in this talk that at least part of the solution. What you have then is people wanting to have panic about electric vehicles. I don't know why. Some people then post things like this. Oh, well, the electric vehicles will never fit in our electric grids, and they're just going to destroy everything, make everything more expensive. And for a while, our local system operator here in Berlin was actually not caring so much about it. But then 2 years ago, 3 years ago, they were like, yeah, okay, so maybe now some electric vehicles are coming. Everybody's going to tells us our grids can't do it. And they ask us, can you simulate that? What would happen? And then there's one thing you have to kind of understand, because like I said, let's say in this institute like that Mark works for, similar mobility institutes, they made some sort of scenario and said there's going to be so and so many vehicles in 2030 in the city of Berlin. And they also can, then from that you can derive kind of a scenario of how many charging stations you need. Let's say we need 1,000 charging stations, and then each of them has like 11 kilowatts. So why not just put in enough cables to have 11,000 kilowatts extra space in the grid? Well, this is not how system operators work. And that's actually how they don't do it right now. So for example, in your street, if you and your neighbors all agreed on, let's say tomorrow at 5, you want to plug in all your hair dryers, turn on the oven, and start vacuuming, you will have a like a blackout in your street, because your street can't handle it. Like even within your own household, like plugging in everything, you're gonna break your fuse, and you can't have as much electricity, because if we would want to plan for this case, we would have need much more cables in the ground and also within your house and everything. So there's something that's called concurrency that you're kind of planning for. So you're kind of expecting everybody dries their hair at slightly different times. For some people, like I don't dry their hair. And that's why you have the sort of averaging out of load. So this is the same which happens for electric vehicles. So when you increase the number of charging points, you have this sort of, on average, decrease of the peak load. So if you have a charging station of, let's say, 11 kilowatts, if you aggregate 100 of them, on average, they only consume 2 kilowatts or something, like on the higher aggregated level. So now our system operator then basically wants to know, okay, what would happen if somebody wants to have a garage of 20 charging points, what it would look like, or they also want to know for whole Berlin, what would it look like, so they kind of can plan their systems better. And for that, they kind of asked us, and do you have some data? What can you do? So we thought about 2 ways of approaching this. One was actually using measured data, and one was simulation. Let's first look a little bit of the measured data. So we've been working, like I said, over 10 years now in electric vehicle projects. And this is actually some data here from one research project. This is from the EUREF campus in Schöneberg, here in Berlin. You may know this. It's a nice campus with a lot of companies are working there that are working on energy, also the Deutsche Bahn, Schneider Electric. And there's a ton of charging stations, and we had access to the data. So this is actually what I kind of expected. So you see in the middle, this gray box. So because it's an office area, so you have in the morning some sort of peak where people arrive, plug in their car, they charge, then the cars are done, nothing happens, and at the end of the day, maybe some cars of some salesperson still comes back, they also park, and then they leave. So this was kind of what I expected, but what I saw in the data was this, like in the middle of the night, there was like giant peaks of cars charging there. Like there's actually some days where this is really small, and I ran some outlier detection algorithms, and it was flagged as outliers, and I was kind of thinking, what's weird? Did I pass the date timestamps weird or something? Did I do any mistakes? Because I just couldn't explain it. And then I asked the people what's happening here. And so this is actually, I don't know if you remember, in Berlin, there was Clever Shuttle, which is like a provider of, it's like a shuttle service, a pooling service like Uber with electric vehicles. And they were charging there. So they were dropping people off on Saturday nights, and at 2 or 3, they then went to the EUREF campus and charged. So then I was, okay, this sort of data I can't use, because it's not even now representative anymore at this location, because this sort of provider is not charging there anymore. So we can't really use this to gain any knowledge about Berlin. So then there's one project that I want to point out. It's called Neue Berliner Luft. So this is one project where we and some partners wanted to install 1,000 charging points, and especially many of these very cheap charging points, for example, also in lanterns of the company Electricity. By now, there should have been already a few hundred of them, but because things are hard in Germany, out of reasons that I can't address here. We only have a few of them right now. Hopefully in the next years we can get up to 1,000. And of those, the idea was to get real data of really very different people and then also do some data analysis with this to kind of do this sort of analysis that we're interested in. We don't have this data yet, because then we could, I don't know, take, for example, some measured events, sample some more events that follow these sort of distributions with different, we're also looking at guns and other machine learning methods there, but we can't do it yet. We don't have this data. So let's go to simulation. And this is where I promised the car. Because we noticed that electric vehicle infrastructure simulator kind of abbreviates nicely to ELVIS. So we needed a logo for that. So this is our electric vehicle with like this hairstyle. And so this is basically what it does is it helps us to answer these sort of questions that we have faced in our research projects. So what if everybody in Berlin uses slow or fast charging? How will different parking spaces look like if like a supermarket has a charger, or some parking garage, or some residential buildings, some office building? How will the grids look like, and how much can EV batteries increase solar energy self-consumption and so on? So we have really all these sort of different questions that this tool can basically help us. We're actually wanting to open source it at the beginning of next year, so you can also use it. We do everything in Python actually. Oh, yeah. And then basically what it does is it uses mobility behavior assumptions, some assumptions about the charging infrastructure, and then basically what it does is it acts like people charging. It's not rocket science, but there's a lot of knowledge also built in there on and that can be configured. And so it's like I said, it's not rocket science, but you can check it probably out at the beginning of next year. So we do everything in Python. Maybe one, I think scikit-learn, TensorFlow, some of you have used before. Maybe one interesting is Panda Power. It's building on pandas, the pandas data frame, and then uses the pandas data frame to model electricity grids. It's one nice example of of a very specific Python package. Maybe one that is also not in the average data scientist toolbox is Padgham. So this is one of the slides that I put in now that I have more time. Just this could be actually more in your toolbox if you ever have to do optimization. So because it's kind of nice, because it gives you some sort of nice syntax when you're kind of used to these mathematical expressions up there. You can model the objective function kind of similar to that, or you can model your constraints like this. So you can check it out. It's pretty nice, and it helps us to do some sort of optimization things, just as a side note. But what I want to talk about is mobility behavior and how we model that. First of all, just some more background knowledge. So electric vehicles will not be used like regular combustion engine cars. At least I believe that. So you can't just go to like a gas station because there's no gas. And what you will do is you kind of charge at different places. So one thing that you will do is this sort of, which is called periodic charging. So you will charge where you park anyhow for long times. I mean, most of the cars are parking 95% of the times. And there you typically don't need so high power. So this could be those sort of lanterns of this partner, but it could just as well be a wall box in your garage. Then there's the sort of additional charging. It loses a bit of relevance a bit, but it was actually what was funded over the last 10 years the most, I would say. So this is the sort of charging stations you see around Berlin. They typically have 11 to 22 kilowatts. So here the idea is you go shopping for an hour, or you go to your gym for an hour and you just charge a little bit. It will not be enough to fully charge your car, but if you do it every once in a while, it may still be enough to get you around. And then there's the sort of fast charging hubs, which will be more importantly on the highways, but they may also be in the city. Typically right now there are 100 to 120 kilowatts that what a Tesla can do and what an Audi can do. But in Berlin, there's actually one charging station with 350 kilowatts where there doesn't exist a car right now which can do that, but they already installed. Just to give you the sort of range, so you see from 3.7 kilowatts to 350, so that's quite a bit of differences. And we kind of want to simulate all of that. So where did we look for data? So unfortunately, We didn't hear about the Deutsche Bahn, but Deutsche Bahn, for example, put up some open data. So that was nice. We actually used this data before. We had this actually before this data was open sourced in one of our research projects. So we used that. Similar, a few years ago, if you've been in Berlin, there was these multi-city cars, if you still remember then, what we did there to get this data, because there wasn't an API or something. We did some web scraping. Similar, Car2Go, they actually provided an API, and so we could get this data. So this is just 3 different ways how we get some car sharing data, for example. So we logged this for a while, put this into databases, and used this to do our sort of simulations. The problems with this is it's all car sharing, and I'm not as optimistic that in 2030, for example, all cars will be car sharing. So this also doesn't generalize to all the use cases. So you can use it to get some sort of ideas for certain areas, maybe. But we could use it a little bit to do some modeling at least. Yeah, we heard already about this one company, and I told you about this sort of additional charging. And one idea we had, okay, if we have a supermarket like here, this Lidl in Schöneberg, we have in Google this sort of thing down here, which basically tells you when people typically are going shopping. And we kind of assumed people will do this similarly also in the next years, and also if they have the electric vehicle, and then kind of assumed when people arrive there with a car, okay, we don't know if all these people arrive with the car actually, again, some assumption. And would it be nice to use this at least to kind of see what we can expect there? So this is something what we did. Problem, this is one of the most requested features in the Google Maps API. It hasn't been included yet. Since it hasn't been included for years, I think Google has good reasons not to do it. There is some Python package which can get you this data. Problem being that you violate Google Maps terms of usage, terms of service, and you can get blocked by Google. So I will not tell you if we ever use that data, but obviously you have to be knowing that you do that. Yeah, talking about Google, just one not so serious attempt of also getting data that is not open. So we once had the idea, we wanted once to simulate what would happen within one street. Actually, it's around the corner here at TU Berlin, where we had the grid data of our local DSO. And we wanted to know what would happen if every parking spot had a charging station. What would happen in the street? So what we did back then was send out our student and have them count, because we looked if we can find it in some open data, like we looked on OpenStreetMap, we looked in some GIS portals of Berlin, didn't find any counts of parking spaces actually. So what we then had one idea in a hackathon once was, okay, how about using Google Street View and just counting cars? So the idea being to write a piece of code which basically writes down the street, looks once to the left, looks once to the right, and then you use some object recognition algorithm to count cars. And in areas like Prenzlauer Berg, Schöneberg, and so on, there's never a parking spot that's empty for long. So we kind of assumed should at least be some approximation. Yeah, so we had this sort of pipeline where we downloaded addresses from an area from like some open Berlin open data portal, traversed the streets, counted the cars, and based on that calculated what would be the load on the transformator. It worked with okay-ish accuracy. We never really evaluated it that well, but yeah, still it gave us at least some nice stuff to play around with. Actually, yeah, this is still my water bottle that I got there. So yeah, was fun, but not so serious. Then one more serious thing. So I think we already talked about mobility data, mobility studies. So in Germany, indeed, there is mobility studies. They are often very local. So there's some studies which are focused on cities, for example, which is called Mobilität in Städte. One problem there is they provide the results in hundreds of pages in PDFs. So that also means you need student researchers that can help you put it into formats that you can. Similar, here's a very local study from Alasto. Yeah, similar problem. We had to kind of get this out of the PowerPoint slides or the PDF reports. Then there's one very big study. This is what we had in the talk with Mark. This is the sort of study where they ask people for a week, where did you go? And you have them have diaries. And this is one of these studies where, okay, I tried to get this data, and it's 100 euros you have to pay, which is not so much. So as a research institute, it's usually fine to get this sort of money. But then you have to fill out a bunch of forms. You have to sign that you, so there was a signature needed by some privacy responsible person, your institution. So I asked the TU privacy responsible person, I don't know what the position is called, and she asked me to prepare like a big privacy something concept. And after having some calls with a bunch of emails, I at some point just gave up. And so yes, this data exists in Germany. It's a very good source of data, but I don't know, like for me, it was demotivating using it, especially now that I, like Free said, worked with the Barcelona equivalent data, which is very similar data that we used in the local chapter of Berlin for Barcelona to do some analysis on gender difference, mobility. I kind of wished it was like that in Germany. Okay, concluding on the mobility part, and then maybe 2 or 3 more minutes on example results. So yeah, due to sector coupling, the mobility and the electric grid kind of come together now. So mobility data is also very relevant for research like we are doing. E-mobility data that does exist does not generalize so well. It's mostly from smaller use cases, from early adopters, from car sharing fleets. Publicly funded mobility studies exist, but I find they're not fun to use because they're either in PDFs or hard to get. And one big but is also that they're based on combustion engine cars. So you still have to put in a lot of assumptions. For example, just because somebody arrives at home, let's say every day at 5, will they also plug in the electric vehicle every day at 5? So this sort of assumptions you still have to make. And what we do usually is, okay, we assume, for example, they plug it in every day, or we assume they plug it in every 3rd day, only when they have to charge and this sort of stuff. Yeah, private companies, like we already saw, they have a lot of data, but yeah, it's seldom easy to access it out of different reasons. And then one point, not so important right now, so there's also long-term uncertainties, right? I mean, it's not clear what mobility looks like in 20 years or 10 years, especially the electricity grid operators. They are usually having planning horizons of 40 years. So when they open once the ground, they want to know how much copper to put there, and they don't want to open the ground for the next 40 years. So within the next 40 years, like if you look, for example, here, automated driving, autonomous driving, or everybody uses their bike, like there's just so many scenarios where we can go to, and we don't know that. Just very briefly, some of the what would results look like. Well, you can, for example, just have like this sort of residential building and a fast charging hub. And in both cases, we have 20 chargers. For a residential building, you kind of assume people arriving once a day, parking, staying overnight. So here we have even a little bit more. And then you see, okay, it's not so high impact. But if you have the same for like a 20 charging points for like, let's say, one of these fast charging hubs, you kind of assume a lot of cars coming, like in a gas station, one car comes, charges, leaves again, then you have a lot of more events, and then you have easily 2 magnitudes or one order of magnitude more. Just because, and then here, like typically, like your transformer would be 1 megawatt, so you would kind of, in this case, not be able to handle this. And then there's also differences, like on residential buildings, you can do control charging because it doesn't matter if it's done within the next hour or so. But here you want to have it charging as fast as possible. One other example where it was not about the impacts, but also about the chances was, okay, this is very hard to read now, I think, but here, like sector coupling, I use this term. Now in the future, you can not only couple like something like photovoltaic systems and the electric vehicles, but also the whole heating part. So what is now provided by here gas, gas, will soon also have to be provided by electricity, as we saw earlier, like in the big pie charts to get the CO2 out of our systems. And yeah, so now things are coupled. So you have things like a CHP or like a power to heat. And now you can have a lot of degrees of freedom how to optimize things. One example result, for example, is from one case study, like if you, for example, combine different things, or you do like the uncontrolled charging, you can get like around 68% of your locally produced PV and CHP energy into cars. If you allow some controlled charging, so you say, okay, don't charge immediately after plugging in, but kind of do some optimization on when is the best time of day. You can increase that number, for example, by 8.5 percentage points. And then something that's often discussed is that cars can also feedback the energy. For example, charge when there's still solar power, and then discharge when people are watching TV or whatever. But here in this case study, for example, and this is something we often see in our case study, this actually doesn't add so much. So you don't have as many new degrees of freedom as you kind of wish for. Yeah, this is just one of the many results that I can't present today. But if you're interested in that, yeah, contact me and we can have discussions about that. Okay, thank you.